Good morning, everyone. Thank you for joining us today for our What is Power Quality and Why is it Important webinar. My name is Lorena, and I'll be hosting today's webinar. Throughout the session, I'll be monitoring chat and conducting some poll, and I'll talk about that in just a little bit. But today we'll be covering some fundamentals of power quality and why is it important at your facility or for those who work with customers. This is our only webinar that we're offering for an hour and a half, so we won't be taking any breaks because we want to cover as much as we can, and but feel free to take breaks as needed. We also want to thank our co-sponsors, Energy Trust of Oregon and Northwest Energy Efficiency Alliance, which you'll see their logos at the bottom of the screen. Based on our customer feedback, they appreciate that we're aligned with them in delivering our messages so that there isn't any confusion around that. And before I introduce the instructor, I did want to point out a couple tools. We want today to be interactive for you. So you'll see to the right side of your screen, there's a participants window where all your names are listed. And there's also you raise your hand icon if you have any questions throughout the session. We do have 10 minutes dedicated at the end of the session where we'll hold all the questions till then. But if you have something you really have to share or ask or need clarification, feel free to use the little raise hand icon underneath all your names. Right underneath that, you'll also see a chat window, and that's where you can chat the questions or any issues that you run into throughout the session to me, and then we'll address it then in the session. I'll address it as I can as we go through. We're also going to be trying a video later today, so hopefully that'll work for us, and if not, let me know. We will be sending the materials and the recording of the session along with the video within a couple days, so you will get anything that you might have missed if you logged in late. And on that side of the window, at the end of the session, we'll also be doing a polling survey and collecting some information from you on how you thought our session went. I also want to point out on the top left corner of your screen, there's these what we call annotation tools, and I'm drawing a line here. They're located right above that red line that I drew. There's an arrow, a T, and some other tools that the instructor will let you know what to use in each slide so that you can participate and give him more information as well. So I'm going to introduce Gary Larkins is the president of Advanced Power Solutions. He has over 25 years of experience in power system analysis, testing, design consultation, training, and commissioning. He also is a licensed electrical supervisor with over, again, 25 years of experience, and is a primary author of Power Safety Pro, which is an electrical safety program template that's used by organizations across the U.S. for basis of their written electrical safety program. He has also completed over 250 power quality consulting projects with utilities, industrial, data center, institutional, and commercial clients. So Gary, we'll go ahead and have you get started here.
Okay, thanks, Lorena. Well, welcome everybody to the webinar, What is Power Quality? I appreciate you all attending today, and we are going to take a quick overview of power quality today in the next little over an hour, give you an introduction to power quality. Now, as we go through power quality, realize that we are condensing this material down to a little over an hour. So in many cases, we would have an 8-hour class to give an introduction to power quality. So we're just going to cover at a high level some of the subjects on power quality. Well, please help yourself to some healthy virtual goodies and refreshments. Of course, the electrons making this digital latte possible are brought to you by PGE. Sorry, had to introduce a little humor there this morning. Well, a little background on myself. As Lorena indicated, I have years of experience in power quality. I've completed over 250 power quality consulting projects, including lightning protection for AT&T Wireless, and I teach electrical courses, including hands-on power quality labs for the Western Energy Institute. So today we'll review what is power quality. Why is it important? The types of equipment that may be impacted. We'll talk about the power path from power generation to your equipment. We'll talk about utility and facility considerations, power quality anomalies. What are the types of problems that you might see, the anomalies and the problems they create? How to avoid those problems. If you have something that you suspect is a power issue related to power quality, how do you resolve that? And we'll introduce some case studies. And if you want further information or additional training, we do have an upcoming seminar on September 28th. That's an 8-hour power quality seminar that offers CEUs. Lorena will give us more information on that at the end of the seminar. So please use the tools to tell us a little bit about your job function here. In the upper left-hand corner, you'll see there's a pointer tool. If you could use the pointer tool and then just click on the rectangle here. So I will use that to show us a little bit about what your job function is here. Okay, I see we have some folks in energy efficiency and consulting. We have engineering and consulting, some folks in facilities management, and other categories as well. Thank you for that feedback. Okay. Great, thank you very much. Some additional folks in energy efficiency. Good. Okay, more coming in here. Thank you very much. This helps me get a background on what type of job function that you have and the different interests that you may have. So if you would now give me a little indication of the facilities you work at or in. What type of facility do you work at or? Okay, we have industrial manufacturing, institutional. Okay. Quite a few in the other category. Great. Thank you for your feedback on that. Okay, what do you hope to learn today? We have get introduced to power quality, how to avoid problems, problem resolution, or maybe something else, maybe just attending for a refresher. Okay, approach to problem resolution seems to be a key one here. Okay, we will definitely discuss the introduction of power quality today, and we'll talk about problem resolution. Thanks again for your feedback. So let's talk a little bit about market trends today. We see electronic equipment and controls are increasing in facility, and this is absolutely necessary. We need additional control. We need energy efficiency in the marketplace. So as we start introducing new technologies into especially existing facilities, we see sometimes there are things that don't work as we expect them to because we're bringing new equipment in and putting it in a facility that maybe has been around for maybe 5, 10, 15, 20 years. We have rapid development and introduction of new technologies. In fact, the time from the development of a product to the marketplace is becoming shorter and shorter, where products are being developed and introduced and put out in facilities. And then sometimes it's kind of like version 1.0 of a software. I don't know about you guys. I love technology, but sometimes version 1.0 of a software means that you're going to be seeing some of the issues around that new piece of equipment. We have a high dependence on reliable electrical systems today. Some facilities operate 7/24. We have just-in-time manufacturing, and many facilities have a high cost of downtime or loss of use, or in some cases it's a safety issue, such as a hospital where patient care is a big concern. An example of this is adjustable speed drives. As we implement adjustable speed drives into facilities for improved energy efficiency and process control, this is a great way to save energy. However, if the drive is not properly specified, installed, etc., we can end up with issues that we never expected to end up with, and that's really not necessary. Those things can be avoided by proper design. So we have today, photovoltaic systems, LED lighting, lighting controls, of course, electric vehicles, all being introduced in, and we have compatibility concerns between this equipment and the electrical power system. So what is power quality and reliability? Well, it's really the ability of the power system to deliver power that's within the operating tolerances of the equipment. Now, this doesn't mean it's all about the power delivery system. In many cases, it's the tolerance of the equipment that you install on the electrical power system. In other words, if I buy a drive, is it designed to operate with the level of fluctuation in power that I have on my power system in my facility? That fluctuation may come from, variations in the power grid. It may also come from fluctuations that occur, let's say, by startup of a large load within my facility, which may cause what's called a voltage sag. Okay, power quality also, when we're looking at it, it provides for a level of performance and reliability that can be justified by safety concerns, such as the hospital I mentioned, economics, because again, we accept some level off of perfection because of the economics of getting to the level of perfection that we're looking for, or other impacts to the organization. When we look at power quality, what we're trying to do is match our power grid or our power system in our facilities with the tolerances of our loads the best we can so that we don't end up with problems. Also, we're trying to avoid interaction between equipment and the facilities. Let's say maybe I have a backup generator in my facility, and when I start my drives or start my motors, I cause interference with the way the generator feeds other loads. So this is something we're looking at, compatibility between systems. Well, today, businesses rely upon electronics. Just about everything today has a microprocessor control or power electronics in it. And again, this is great. I love technology. But we also need to be concerned where we're replacing older loads with newer technology systems. What about this compatibility issue? If I go buy a piece of equipment from a manufacturer, is it truly compatible with what is happening on my power system? So here's just a short list of some of the different types of loads that we see in facilities now. And we're even introducing more electronic loads, especially as we're looking at electric vehicles and more electronic controls. Here's just an example from a server manufacturer, their tech note, regarding types of power problems. This goes out to their technicians. And they indicate here that environment, power line disturbances, surges, power line transients, electrical noise, high frequency noise, or defective grounding and ground potential differences are some of the key concerns around intermittent problems that they may experience. So they point to their technicians to look for these types of issues. So I'd like you to, again, take your arrow, your pointers up here in the upper left-hand corner if you click on this, and then tell me, have you or any of your clients experienced any of these symptoms associated with power quality and reliability issues with electrical or electronic equipment, such as unexplained failures, maybe failure to perform as designed or specification, malfunctions, including intermittent malfunctions of equipment, catastrophic failures, where you see equipment, as we see in the upper right-hand corner, we see an example of a catastrophic failure. I was doing a project in Utah where they actually had the equipment catch on fire, okay, because of power quality issues related to internal to their facilities, or higher failure rates than expected. You may expect this equipment should last for maybe operate successfully for 5 years, but maybe every 6 months or so you're seeing a failure. These are all things that help point towards power quality issues, potential power quality issues in a facility. Now, of course, we have other issues as well, software errors and so forth, that we have to take into account. And great, thanks for the feedback. I see we have a mix here, everything from unexplained failures to failures perform as designed, higher failure rates, and catastrophic failures. Thank you for that feedback. So why do we have issues? Why do we have issues on systems? Well, electrical systems may not be designed to provide power that's within the tolerance of the connected loads. So in other words, let's say we design around a certain piece of medical equipment, and we picked it because of its characteristics to perform medical functions, such as x-rays or so forth. Is the power system in our facility designed? In other words, have we designed it? Let's say we put a backup generator on this. Is the output of the backup generator going to provide the output of type of power that's necessary within the tolerances of that equipment? Or you may have an electrical system designer that may not have specified equipment that operates within the power delivery system tolerances. So to break that down, for example, I'm going to go out and let's say specify adjustable speed drives to a facility. Do I know what the level of fluctuation of power is coming into the facility? And I'll give you a case study example on that, where it's important we understand what's happening on the power grid before we, and in our interior facility power systems, before we go out and buy equipment so that we can help ensure compatibility. The company that designed electrical utilization equipment may not understand the electrical environment. In other words, did the organization that designed that hardware, and again, I'll give you a case study on that, do they understand what the power system, the fluctuations look like, the types of anomalies the equipment may have to handle and successfully operate? And system and equipment availability and reliability may not be adequate for your requirements. Well, here's an example, this graphic down here at the bottom. We can see that Hartford steam boiler, they consider line disturbances such as power surges and other conditions now the leading cause of equipment breakdowns. So this is an insurance company that tracks equipment breakdowns because they're going to pay out on claims, so they understand the number of failures and look into many of the major failures that are seen. Again, why do we have failures? In many cases, when we look at new facilities or major installations or remodels, you have a new construction team and accounting department that are kind of driving things in many cases. In other words, how fast can we get this done? How can we keep our costs down? But yet, driving on speed and cost without the focus on the actual long-term operation of the system may not give us the best focus for our long-term look at the system. On the other side of the equation over here, and it's kind of a tug of war, you have operations, facility engineering, maintenance. They're focused on reliability, making these systems work that may have been designed around low cost initially without taking into account how this is going to operate in the long run. I would always suggest that if there's an existing facility, that the folks that are in operations or facilities engineering, they get involved with the new construction team or accounting or a new construction team to help guide what equipment is installed. So when it comes to power quality and reliability issues, one of the things that we want to look at, whether it's a new facility and we're trying to decide, okay, how much do we want to spend on protecting or putting in what you would call mitigation equipment, and it's harder for a new facility where you don't have maybe a track record, or it's an existing facility especially, what is the cost of the loss of use of that equipment? What's the potential cost that we could incur or that we are incurring? This is from an actual case study here, where this organization, every time they went down, they had a loss in productivity of $12,000 per event, and the basis is shown over there on the right. They had about $25,000 in equipment damage. So $12,000 in lost productivity, $25,000 in equipment damage, and about $8,000 in scrap. They also had some lost sales, okay, that because of orders that went to another firm due to a lack of stock. They were shipping out just about as quick as they could manufacture this, and in many cases, if they couldn't fulfill an order would go somewhere else. So the total cost for a power quality event was about $50,000. They averaged about 10 events per year, so providing an average annual cost of about $500,000. So we're able to look at a solution that solved about 90% of the issues. Why not 100%? Because getting to 100% was not cost effective. The payback would take too long for their capital investment rules. So we're able to solve about 90% of the issues, costing about $150,000 to solve this, saving about $450,000 a year. When you look at the simple payback, that was approximately 4 months. Some sites have personnel safety concerns where it's not just the cost, it's also human safety is at risk or of concern. Here's a quick case study here. I recently completed a project. There was a large airport decided to upgrade their escalator system to achieve their energy efficiency goals. Very, very important. They were spending a lot of money driving these escalators with standard motors and low-tech controls, wasting a lot of energy. So they looked at a new energy-efficient technology for their escalators, including soft starters, adjustable speed drives, and electronic controls. There was significant energy savings potential, which they'll realize. But upon installation of these escalators, they found their new escalators are tripping offline. And you can imagine if you're on an escalator packing a bunch of luggage and all of a sudden it comes to a stop, that's not a good thing. So sometimes there were issues with personnel safety as well here. So the problems were chased for months. The contractors and the equipment vendors chased them for months. They suspected power quality issues, but they couldn't pin them down. The power quality monitors that they, or analyzers as they called them, that they were using were not capable of seeing the disturbances that were causing the shutdowns. I was brought in to look at the situation. The facility believed that their power was within the normal range. The equipment manufacturer believes its power excursions are excessive, but they do not provide any published power requirements to the owner. So here we have a facility that believes their power is normal. You have a equipment manufacturer that believes the power excursions are excessive, but they have no published guidelines. So who is responsible here? Who's responsible to make this work? Who will pay for the corrections that may be necessary? And the interesting thing here is the accommodations could have been made during the design phase to prevent this interaction issue. This is a known issue that can happen, an interaction between electrical systems and the equipment, and it could have been prevented by more careful specification and information on the front end. So all of this issue could have been avoided. Let me give you a quick analogy here. We have a four-wheel drive vehicle. Now you go into let's say, a dealership, and you say, I want to go out and I want to do some four-wheeling. The salesman says, okay, we have the perfect vehicle here, four-wheel drive, vehicle of the year, Motor Trend, etc. So here's the vehicle you need. However, you don't tell that salesperson that, let's say, I'm going to take this mudding. I'm going to go out in a foot, foot and a half, 2 foot of mud this weekend. So you buy that vehicle, you drive off with your four-wheel drive, expecting it to work fine, except it has street tires on it. In other words, the four-wheel drive may work fine in the snow, may work fine in, let's say, 6 inches of mud, but now you're going out in 2 foot of mud without the proper mud tires on it. So you get stuck. Now, who's at fault here? Were you at fault for not telling me what you're going to do with the vehicle? Was it the salesperson at fault? Or was it the manufacturer that said this was a great four-wheel drive, could take you anywhere you wanted to go? You see what I'm saying here is that information needs to be discussed, the use of equipment, etc. Properly equipped, this vehicle would not have had a problem. So this is why we need to look at the bigger picture. So from a utility perspective, some folks are not fully aware of what happens on a electrical power distribution system. We have power generation. The power may take hundreds, if not thousands of miles to get to us from the power generation facilities, where we have generation remotely located. We have transmission lines to where we have to transmit maybe at 345,000 volts. We have exposure, and you can see here I have a little graphic here of a raptor. When I worked for one organization, we had raptors building nests up into the 345 kV line, which when it faulted across the insulator, when they got contamination on the insulator, it would bring the whole grid voltage down in the valley. You have lightning that can strike, whether it be a substation or power lines. You have windstorms, tree limbs, car hits, pole. These are all things that can contribute to power anomalies on the power grid system. And these are a natural operation that can occur because we have exposure out there. Utilities have voltage ranges they try and stay within. In fact, they're guided by national standards. For an example, ANSI C84.1, it has 2 voltage ranges, and I'm giving you an example of range A. But if we look down here, we see the range A minimum voltage and maximum voltage. And this is the phase-to-phase or phase to neutral voltage here. We can see on the low end, their target is 456. On the high end, it's 504 voltage. There is also a range B during abnormal operations, such as we might have storms or something else that causes anomalies on the power system. But in many cases, folks aren't looking at this fluctuation, the possibility, even on a steady state basis, we could have a lower voltage than, let's say, 480 volts on our nominal system. And for short-term type events, such as faults on power lines and so forth, we could have excursions down even lower. So what do these excursions do, and why do we have these issues? Well, let's say lightning hits the power grid right here. In order for that power grid not to continue to arc and burn and to continue to protect the conductors, kind of like a circuit breaker in your facility or your home, there is what's called a recloser. It has to open up and stop the fault from occurring up here. So what this does is this opens up, maybe 6, 8, 10, 12 cycles, opens up, and you've probably seen the lights blink before, whether at home or at your business, the lights blinked and then came back on. That's that recloser opening up to protect against the fault, okay, to keep the system from causing, let's say, a meltdown in the conductors. So you might see an interruption here, or if downstream you have a fuse on your feeder, it actually may cause an outage. Now over here, out of the same substation, let's say the same transformer, this bus here, a local utility substation, the source where many feeders come out of to feed different areas, when this fault occurs, it's actually going to pull the voltage down. So your feeder may experience not the interruption, but the voltage sag. This again is the normal operation of the protective functions of the power distribution system. And Lorena's going to show us a video just representing failures, such as we see in power systems. You've probably had a motor fail in your facility before, or some type of equipment failure. Well, there are failures in power grids. There's failures in all different types of systems. So we'll take a look at this video and see what's happening here. And this is actually at a golf course in Florida, where they caught this transformer, and we can see the transformer. This is a catastrophic failure. It doesn't occur that often, but if it does, how are you protected against what may be sent into the power grid here from this type of event, this type of failure? Do you have adequate protection? I've seen transformers within customers' facilities, their own transformers, do this same type of thing and actually cause, in one case, a whole computer lab. They failed equipment in an entire computer lab because they didn't have adequate protection. So we see the transformer over here on the left. That's the resulting view of the transformer. On the upper left here, we can see that here's an underground splice, and these splices were failing at different locations, causing arcing faults. So there's exposure from the utility side. The utility has steps that they can take, and they generally implement these steps. They're very conscious about power systems and reliability and availability and power quality. So tree trimming, animal guards, protection from contaminants, maintenance, changing settings, etc. There's many steps a utility can take, and usually they're very proactive. And the utilities generally keep track of their reliability. In other words, are they seeing interruptions? And they track these. In many cases, they report them to the Public Utility Commission. How are we doing? Are we keeping our customers in power? What's our reliability look like? And here's just a sampling of some of those indices used by utilities. Okay, how about in facilities? What do we have in facilities? Well, maybe I have a large chiller without an adjustable speed drive. Every morning at 7 a.m., that chiller comes on, and it causes a voltage sag within the facility. So again, I have to look inside my facility as well. In fact, in many cases, the majority of power anomalies we see come from within the facilities themselves. In many cases, we've had somebody install new equipment, and they didn't understand how it was interacting with the other equipment. So you have motors, adjustable speed drives, UPS systems. All these things have to play well together in your facility. Just to give you a quick example, we had one place where they were a robotics welding equipment manufacturer. And what they did is they installed these new robotic welding machines. So once they started operating these machines, all the small UPS systems in their office that was fed off the same power transformer started going to battery backup because they were creating sags when they started welding. The solution there was not a utility solution. It was actually a facility solution to put equipment on those robotic welding machines that would slow down the inrush of current to those machines, allow them to operate properly but not cause major sags. Other exposures, we have loose connections. In doing inspections, that's one of the largest causes of intermittent power issues or transients we see in facilities in many cases is loose connections. Improper or poor grounding, a mix of critical and disturbance generating loads. In other words, going in, putting something on that creates a disturbance. Load switching, such as bringing on large chillers, wiring errors, faults, automatic transfer switches. And over here on the right, here's a graphic. This is from a hospital where their elevator contactor serving their motor, this was not fed by an adjustable speed drive, by the way, it's direct from a contactor to a motor, was actually causing this disturbance. Even though the disturbance wasn't high in magnitude here, and here's the AC sine wave here, this is the disturbance right here, and it's a lot of transients right there, not higher than the peak voltage here, but what this was doing is causing the surgery suite controls to fail. The biomeds had just a stack of boards that they kept fixing and replacing. Of course, this was not a good thing when it caused the surgery suites to go up to 90 degrees right in the middle of surgery. The solution for that was proper surge suppression and filtering, and also replace the contactor with one that wasn't as pitted. Newer contactor also helped with that. Here's another facility, an example from another facility where they installed a new system, didn't pay attention to the interaction between the equipment. As we can see, and going back to the previous slide here, we can see this is what the waveform should look like without all this interference right here or this transient. Going here, we can see this waveform doesn't look anything like what that waveform looked like. So we had significant overvoltages because of interaction between the equipment and the facility, and that could have been avoided on the design phase. So why do we have failures? Why do we have failures and intermittent issues with power quality? Well, one of the things, when we get down to the digital chip level, and this is just showing you an example of digital chip here, and we can see it on the upper right-hand corner here where we see there's actually a failure here where the insulation broke down and it arced over. You have logic level signals. Microprocessor chips operate at about 0.8 volts. You have logic level signals here where a logic on may be 0.6 volts on a 0.8 volt chip, where you may have noise or transients that get inside the equipment that actually cause a false turn on that microprocessor. Now, if the voltage goes high enough, that's where we see the breakdown here in the microprocessor. So this can be either intermittent errors or lockups, or it can be a full failure in that microprocessor. So let's talk a little bit about power anomalies. So what is an ideal sine wave? It's one that really makes the equipment work. Okay, there isn't perfect power, not out of a generator, not out of a UPS, but we can see here we have a sinusoidal waveform. Now let's look at some of the anomalies. We'll start with surges or transients. Now, when I go through these anomalies, we have a lot of anomalies to discuss today. I'm not going to go in depth to these anomalies because of the fact you will get a copy of the handouts, the presentation, so you can look at this. So I'm just going to touch on these so I don't put you to sleep just talking about the different types of disturbances that are out there. But this is a big one, surges or transients. And we can see here, this is a transient right here, or power surge, some people call it. Okay, and this was actually caused by power factor correction capacitors switching on in the system. And this is an example of the power factor correction capacitors that were actually causing those escalators to trip at that airport I mentioned. So whether we have load switching, in other words, we start up a large load, it can create a transient. We have lightning hits a line, it can create a transient. Loose connections. We should have adequate surge suppression should be installed on our system to make sure that we have protection against damaging transients. And when it comes to drives, we need to look at also, and power factor correction capacitors, we need to look at the appropriate mitigating factors, whether it be DC bus chokes or in many cases, line reactors or tuned filters on the front of the drive to help protect those drives from tripping. So surge protection and proper wiring are essential for this. Whether it's in your house or whether it's in your facility, it's important that we protect the electronics against power surges from adequate surge protection. How about sags? Well, if you've ever, seen been in the shower in the morning and someone, started the washing machine, you're probably familiar with the sag. In other words, the water drop down in pressure. Well, this is a reduction in voltage or pressure, electrical pressure, such as let's say we start a large motor, just like starting the washing machine. In other words, the washing machine is not the large motor, but the washing machine draws water through the system, the pressure goes down. So we have voltage sags, and one of those impacts is to cause equipment to malfunction. So we may have to make wiring changes, or maybe we just get more tolerant equipment. There are other mitigation things, as you can see examples of mitigation down there, voltage correction equipment, etc. Swells, that's really the opposite of the undervoltages, where we go too high in voltage. Doesn't happen nearly as often. But when we remove a large load, let's say we have a generator, backup generator with a transfer switch, and a large load comes out, the generator may actually see the voltage may go too high for a brief period of time. Or we could have a large load removed from the system, and it takes a while for the voltage regulator to catch up, maybe a second or so, 2 seconds, where we can see a short-term overvoltage. Now, equipment is less tolerant to overvoltages than it is to undervoltages. This is where we have to be very careful that we're not pushing the equipment too high of a voltage. So I've given you some examples of mitigation equipment there as well. RMS undervoltage. This is more of a steady state undervoltage. In other words, the system has not been designed to provide the right voltage, or we have some underlying condition, let's say. So we may have incorrect transformer taps, or issue with the regulator, or our wiring system has too much voltage drop, kind of like the pressure drop we talked about in the house plumbing, because a lot of loads are on, the pressure goes down. The voltage here again may go down. So we have equipment shutdown, possible overheating or damage, and I've given you some examples of mitigation there as well. In many cases, it's just making some changes to the wiring system or a transformer tap. RMS overvoltage. This is just the opposite of the undervoltage, where we have voltage too high. Again, equipment's less tolerant to an overvoltage condition. So we may see shutdown, or we may see damage. And this may be, only lasting for seconds, but may cause a damage. And then we come back and we look at what was the cause of this? Why was it damaged? Okay, so I've given you some examples, again, mitigation, changing transformer taps, or we may even have to put in some type of mitigation equipment for that. Interruptions. This is a short-term interruption in power, okay, where we may see that we have that feeder operation from the utility because a tree limb touched into the power grid and actually caused the utility circuit breaker or protective relaying system, to open up to take away that fault so we don't melt down or burn up the utility power distribution system. So we can have utility feeder faults. We could have backup generators with an automatic transfer switch that causes this interruption. And generally, we're going to see equipment shut down, but there are some technologies, depending on what we're looking at, to either back up the control systems, or, for an example, an adjustable speed drive could be used here. We use that at one facility. We put an adjustable speed drive in that could restart the motor, sync back up to the motor with the control systems being backed up. And so when there was an interruption, they did not lose their process. Where with a standard motor, they lost their process every time. So I've given you some examples of different mitigation equipment, some things that we may look at here to help protect or to provide ride-through from interruptions. Outages. Of course, sometimes we have that car that hits the pole, or we have a fuse or a breaker trip on our facility resulting in an outage. Now, if we have critical equipment, we may need to have an uninterruptible power supply that can provide short-term ride-through till we can get the issue resolved, or we may have to have a UPS system with a backup generator, or maybe we just have a backup generator there. We can take a short interruption, but we can't live without the equipment for hours if we have some type of, let's say, cable failure in our facility that may take longer to fix. So we have different types of technologies that we can use in facilities, and I've mentioned a few of those, including transferring between two different sources within a facility. Power factor. Sometimes we have what's called poor power factor. We may receive a penalty for poor power factor. This does not necessarily cause malfunction of the loads out there, but it may cause overheating or a loss of capacity use of our electrical distribution system on our facility. So lightly loaded motors are a big cause of poor power factor, high harmonic loads, which we'll talk about. So impacts, of course, utility penalties. We may be losing capacity. We may see excessive voltage drop. So a lot of times folks are looking to go put power factor correction capacitors in. We'll talk about that because when you have harmonics, and we'll talk about what harmonics are here in a little bit, with adjustable speed drives and electronic loads, you have to be very careful about putting power factor correction in. So some mitigation, change to higher power factor loads, install power factor correction capacitors, but with filters where you have harmonics present. So what is power factor? Well, let's say over here on the left side, we see Joe Power Jr. here. Just to give you a quick example of what power factor is. Joe, his task is to crank that handle and make the water flow around his trough. The water's flowing around the trough here, and of course as the water flows, there's friction against the side walls of the trough, slowing the water down, or there are losses. There's resistance here causing losses. But some of that water that Joe cranks around this, that causes to flow around this trough, some of this comes over here and causes this wheel to turn and actually causes work to be done, in this case sawing these logs. This is real work, or the wattage. Okay, most of you are familiar with kilowatt hours or kilowatts that are being used in a facility, translated into kilowatt hours. But some of that, if we have poor power factor, so we have some loads out there that have poor power factor, it means that they're drawing current, which is doing no useful work. In other words, some of that current's going by and not actually causing useful work to be done. And what that is doing is Joe over here still has to work hard. He still has to provide for all these, the water flow through here that's doing no useful work, and crank that. So there's expenses, there's energy expended to do that. So what that is really our reactive power flow. And so when we look at power factor, it's really kilowatts over kVA. Power factor, when you see a power factor penalty, you're being charged for drawing current from the electrical distribution system, from the utility that's doing no useful work, but still costs the utility to create that power flow or that electrical flow through your facility. So when we have harmonics and distortion that can also be present, and many of you probably heard of harmonic distortion. When we hook up loads, let's say we take a standard motor and we go out and put an adjustable speed drive in without filtering or without some of the newer higher pulse technologies. So we go out there, we buy a drive, we stick it in our facility, and what can happen is that load can actually draw current at frequencies other than 60 hertz. If I put a standard motor on, it draws current or flow through the system at 60 hertz. But when I put an adjustable speed drive on, because of the technology used in that, it may draw current at other than 60 hertz. And when it draws current at other than 60 hertz, it can actually cause also voltage distortion in the facility. So we can cause overheating in our facility, on our breakers and so forth. We could cause overheating on the utility transformers. So here we can see this is current flow here from a 6-pulse adjustable speed drive. Now, if that was a standard motor, as the voltage went up here, which is this waveform right here, the current would go up and drop down in a linear fashion. But this is what's called a nonlinear load, which draws current at frequencies other than 60 hertz and causes harmonics. That current being drawn through the system may actually cause this type of voltage distortion as well, especially if we're using a backup generator to supply our loads. So let's look at this. I have fundamental frequency at 60 hertz. If I have current flowing at frequencies other than 60 hertz, and I add that together with the 60 hertz, I actually get what's called waveform distortion. So here I can see the waveform is distorted. It's kind of like adding food coloring in a bowl. I take my 60 hertz, which is red down here, I add some yellow into it, and I get the resultant orange here. So I take my 60 hertz waveform, I add some different frequencies here, which is, let's say, the third harmonic, which is 3 times 60 hertz, gives me 180 hertz. Fifth, 5 times 60, 300 hertz. I add those together, I get current distortion, which may cause overheating of my electrical distribution system and a loss of use of capacity. Also, it may cause voltage distortion like I talked about. Quick case study, one hospital, they went in and put a whole range of adjustable speed drives in without the proper filtering, without paying attention to this. The first time they went to fire up their emergency generator, the output of the generator was not appropriate for their facility loads. In other words, the generator output was very ugly because they hadn't put proper filtering on the drives. So they weren't able to operate a lot of the equipment in their facility due to the poor output of the generator. And this situation could have totally been avoided by, again, by proper specification and installation. So let's look. Here's motor current. This is the current. So current flow, kind of like water flow through a system. The current's being drawn by the motor. Here's the current waveform for motor without an adjustable speed drive. Now, as we can see here, here's the current flow for a 6-pulse adjustable speed drive. And there are drives that have higher pulse ratings, 12 and 18, that have lower harmonics. But we're just going to use a 6-pulse drive for this example. We can see here that the current distortion from that motor here is 3%. The voltage on the source distortion is 2.84%. Now, if I put this drive in to feed this motor, now I can see that my current distortion went up to 80%. So I have current flowing at harmonic frequencies other than 60 hertz. It's actually doing no useful work and causing poor power factor as well. It brings my voltage distortion up over 6%, which may also cause malfunction of other loads fed by this electrical distribution system. Now over here, I've put in a filter in the circuit with a 6-pulse adjustable speed drive. And again, there's other technologies here that could be used. But I've brought my current distortion down to 5%. Although you see a little jaggedness here, it still looks much closer to this than this does. And it's brought my voltage down to under 3%. So by implementing the proper installation, I can avoid the issues. Notching, okay? That's when we may have like an a UPS system, a large UPS system we put on our facility, and it causes these waveform notches. There are also certain other types of loads, such as large rectifier systems, that can create notching. We may have controls, transfer to battery may have a short-term notch. So there are some examples of mitigation down there as well, such as wiring changes, filtering, isolating the sensitive load from the disturbance generating load, etc. Now, what we also have seen in some cases is actually in a little funny case study that there was a large plant that was actually causing notching from the rectifier systems. It was causing the farmers' clocks to speed up because the clocks were using the zero crossing of the waveform to actually control the clock timing circuit. When we had extra zero crossings, we saw those farmers getting up at 3 when they meant to get up at 4:30. Not fun. Imbalance. We may have imbalance in systems where the voltage isn't perfectly balanced between 3 phases. A certain level of that is natural in a system because of just the different loads and the characteristics. But we get imbalance too high and we can cause overheating on motors or cause imbalance in our load distribution in our facilities. Here we see an example, phase B, the voltage is low. Okay, it's about a 3.71% imbalance, typically beyond what most utilities allow of a target of 3% or less generally. And we can see the load here is not evenly distributed from the current flow between the 3 phases, causing extra loading on a phase 2. Phase loss. Here we have an example of we've lost a phase. Let's say a tree limb got into a feeder and it blew the fuse on that phase. Or we had a fuse in our facility. One of the legs in our facility are fusible disconnect. The fuse blew because of fault in the cable. So if phase goes away, we have 2 phases left here. And what this can do is three-phase motors might continue to run if their motor circuit protectors, the proper protective relaying, has not been put in place. So in this case, what we have is the motor may start to overheat if that motor circuit protector. In many cases it will, in some cases it will burn up the motor. So all systems should have some type of motor circuit protector, overload protection, or there should be phase loss relays in there. Flicker. This is when we have loads fluctuating quite significantly. Generally, if we saw the lights going up and down, more prevalent with incandescent lighting here. That's the beauty. Maybe we just change out the lighting system. It's because we have some kind of load coming on quickly, causing the lights to flicker, more of an irritation to personnel. So we might just be able to change out to a fluorescent light or a new LED light and avoid that issue around flicker, or it may take other levels of mitigation on the whole entire feeder. Frequency variations. Of course, for frequency variations, these may come more from a backup generator. Utilities are very good at holding frequency stable. They're tied into a whole grid that requires that. But in many cases, what we have is a backup generator where the loads are coming on and offline, and the frequency may vary enough to where, let's say, like an uninterruptible power supply system may not recognize the output of the generator as appropriate. Electromagnetic interference. This is becoming a bigger issue where we have high frequency noise actually propagating through the system. As we start connecting up more and more electronics, we start seeing high frequency noise that's being generated here. This is an actual welder here actually that's operating in this system that's feeding high frequency noise back into the system. Over here we have a telephone circuit here where the high frequency noise that was on the telephone circuit was actually causing intermittent operation of the modems in a mall, where 50% of the modems in that mall that were used for credit card processing were sitting there because of the high frequency noise. They were actually causing the modem to like pick up the phone line. They would pick it up and then hang it up. So you hear this click, 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 click because of the high frequency noise. This was actually solved, this problem was solved not by having to reduce the high frequency noise, which would not have been easy to do, but actually switching out to a different modem manufacturer. Simplest solution, change modem manufacturers, find out what's working in the facility, change out to those modem manufacturers, the manufacturer's product that worked in the facility. Problem solved, inexpensive solution. So different sources of mitigation down here, shielding, etc. Wiring and grounding. This is one of the most important in a facility. When we do our inspections, we go through and look for wiring and grounding errors. The installation always has to meet the National Electrical Code. We can't have wiring and grounding errors. Even if it was installed by licensed personnel, sometimes errors are made or equipment has an issue inside of it. So if we have wiring and grounding errors, that's going to show up in either failures or malfunction of equipment. We've had whole buildings that were shut down just because of simple wiring errors. They couldn't operate because their communications equipment, they couldn't communicate through the facility because of the communications equipment, because so much noise, high frequency noise and current was going onto the ground system that shouldn't be there because of wiring errors. Here's an example of a waveform, by the way. This is a waveform where we have an overvoltage condition from a loose neutral to ground bond. The voltage should have been, the peak voltage was 280, should have been 170, causing an overvoltage condition, causing the equipment to fail. Performance grounding. In some cases, performance grounding is very important. So we have to look at performance grounding that goes beyond the National Electrical Code. Here we see at high frequencies, we have a low impedance grid where the equipment is all connected together to avoid problems between equipment. But a data center, because they had code-based grounding, but they did not have the proper high frequency grounding for their file servers, and their systems would intermittently shut down. It got so bad that they had to shut down their facility. It was a panic situation. It was solved by going in and fixing a few wiring errors, but also enhancing the grounding system. Electrostatic discharge. Of course, you've probably all been familiar with that. Remember when you were a kid and you kind of took your nice sweater and rubbed it in the chair and ran up and touched someone to see how far that arc would fly? Well, sometimes even small arcs can cause disturbances, equipment to malfunction. Usually you don't even feel a voltage less than 3,000 volts on a discharge. We had a whole medical lab in a hospital that was being shut down by people getting up out of their chairs, which when they moved to their new lab, they didn't buy the anti-static chairs. So when they got up out of their chairs and they walked by the equipment, sometimes they just brushed their lab coat against the equipment, or their body would touch the equipment and discharge, causing malfunction. Of course, this is a major issue when you have blood analysis machines giving out incorrect results. And that was merely taken care of by addressing the static discharge issues. Compatibility. So we might have, again, the interaction we talked about between backup generators, drives, or two pieces of equipment interacting with each other, even a harmonic filter. So this is an example of a backup generator system and a UPS interacting. The UPS itself and the generator were not compatible, thus the waveform we see up here, the generator puts out a waveform that's not acceptable to the other loads that are supposed to be powered in this data center. Drives. Again, here's a little bit of a case study here, adjustable speed drive. In this case, a 6-pulse drive. We take AC input, we rectify it, we have DC here, and now we take inverters that actually create different variable frequency output here to control the motor. Now, in this case, the installation, they did not pay attention to the installation guidelines, which gave a maximum distance between the drive and the motor. So when they did not pay attention to that or install a filter, what we were getting is a reflected waveform back from the motor that was actually causing failure of the motor insulation windings. This could have been avoided by paying attention to the installation instructions or providing a filter, and also the proper specification of the motor would have helped avoid damage to the motor. So have you or any of your clients experienced any of the following? Equipment damage due to power surges. So if you could, again, use your arrow pointer in the upper left-hand corner here and just kind of let us know. Have you specifically seen any type of equipment damage due to power surges, problems with adjustable speed drive installations, or power factor, harmonics, overheating or equipment interaction, shutdowns due to power sags or interruptions, or in some cases we have equipment manufacturers claiming power quality is the source of the issue. Great, I see there's kind of a mix here of everybody having many different types of issues here that you've seen or possibly experienced. Thank you for your feedback there. So, avoiding power quality issues. We all want to avoid problems. So what we need to do during the design phase, a new facility, one of the things we want to know is what can I expect from the power grid? Will the facility power distribution system be adequate? What are the operating tolerances of the equipment to be installed? And this I must emphasize as a major important issue. What is the tolerance of the equipment I'm installing? If I never ask that question, so many times we ask, okay, can it do this, can it do that? But we don't pay attention to what are the power requirements for this equipment? What does it need from a power perspective to maintain successful operation? That alone, asking that question on that escalator issue that we talked about earlier, that case study around the escalators, asking that question alone could have helped avoid a lot of problems. What are my uptime or performance goals? Do I need to change the type of equipment? Or if let's say I'm buying a piece of medical equipment, I really want that medical equipment, but it does not have the tolerances I need to operate it successfully on the power distribution system. What kind of mitigation equipment? What do I need to put between the power system that I have and the load to make the power adequate and to protect that load and to help it operate successfully? And what are the potential side effects with the use of equipment? If I'm going to install equipment or the mitigation equipment we talked about, will it have side effects or interactions? You know, you go to, let's say, a medical doctor, you get a prescription for a drug to help solve an issue, but you pull up the prescription and you look down there and it gives you a list of possible interaction with other drugs or a list of possible side effects. That's the type of question we need to ask. What are the side effects? What are the possible interactions? Maybe we don't have any, but we need to ask the question. So I always suggest writing performance specifications. How do you want the system to perform? Hold manufacturers and the whole team accountable, and then commission the system to make sure it's operating properly. Here's just example of a performance spec. And again, this is just a section out of a page where we've written key performance criteria that we're requesting of a manufacturer. And again, you'll get a copy of this so you can read it in detail. And as part of this process, when we ask for this, rather than trying to read all the cut sheets of, are they giving us what we want, we write clear performance criteria, and now we ask the vendor or manufacturer to come back and tell us, do you comply with our performance criteria? Yes or no. If not, tell us what your deviations are so we can judge whether that's important. So this is an example of using accountability during the design phase, laying out clear expectations, and then making sure that the system is going to perform to our expectations. Remember the four-wheel drive analogy? Again, this adjustable speed drive can be used for improved energy efficiency and process control. But is this specific adjustable speed drive, is it equipped with the proper accessories? Maybe I'm going to have transients in here that cause this drive to trip offline, causing me unnecessary downtime. Why? Maybe I can just go out and buy the right equipment, a different drive, or maybe I can buy the equipment with that drive, the accessories, so it's compatible with my power system. So again, we need to take the system view here. Also, when we look at systems from an overall perspective, let's say I'm going to go out to a facility and I have a whole bunch of motors and I'm going to implement energy efficiency alternatives. One of the things I need to know is, let's say a standard motor here, and this over on the left-hand column of this graph, we see the voltage in percent of normal and the time duration cycles down here at the base. Here we can see a standard motor and contactor may not drop offline until we get down to 50% of nominal voltage. In other words, let's say a tree limb touches a power line for just a brief instant, or a motor starts up in your facility, causes the voltage to sag. Your standard motor may operate through that fine. But when I put an adjustable speed drive in, and in this case, this is from a specific manufacturer, and different manufacturers may have more tolerance than this, but we can see that this adjustable speed drive actually will trip offline around 87% of nominal voltage. So in other words, my motor may have kept on running, but my adjustable speed drive tripped offline. Again, I could take this into account during the design phase and avoid having issues from this. If I don't, I may end up with a surprise. And it's much harder to take care of surprises afterwards than it is to address them in the design phase of a project. So the old saying from Benjamin Franklin is, an ounce of prevention is worth a pound of cure. So we've created an adjustable speed drive checklist that we're going to provide to you. We'll send it out. Lorena will send that out with a copy of the presentation that just gives you some input power considerations, some other things to consider, for an example, applying adjustable speed drive, because this is where we see a lot of misapplication that could be avoided. And there's also a NEMA, National Electrical Manufacturers Association guide for the installation and selection and application of adjustable speed drives. It's mentioned in that checklist as well, and it can be downloaded for free on NEMA.org. So when we have existing issues, and I saw several of you ask about how do I solve existing issues, one of the key things is to document what is happening in the system. I get calls from people, they want to send me monitoring data, but they can't tell me where was the monitor hooked up, what was the problem. So go out, start acting like a CSI or crime scene investigator. Start gathering data and start documenting that data. What do I have? What's happening? What's my system design? Gather my one-lines. Where is the equipment experiencing problems? Where is it operating satisfactorily? What are my equipment tolerances? If I'm going to try and figure out how to improve my power, what grade of power do I need to have to make that equipment work properly? And don't always assume it's a power problem. In some cases, it's an equipment problem. For an example, a hospital had a thoracoscopy machine that was it had been damaged by power events. Well, they blamed every board failure from then on poor power quality. The power quality issue wasn't from ongoing poor power quality, even though they hooked up equipment, test equipment, and tried to prove that it was power quality issues. They hooked up their test equipment, monitored at where their own equipment was creating disturbances, tried to blame it on the hospital's power system. Yes, they had an event. They weren't properly protected by surge protection initially. It caused damage. They needed to replace that equipment. But the ongoing power issue was not related to power quality. It was the fact that they needed to clean out those boards and start over. It was originally a power quality issue, but the ongoing events were not power quality issues because the equipment, proper equipment had been put in place. So we look at economics, safety, exposure, risk. What's the performance from the utility? If you suspect there might be a utility issue, you're seeing a flash in the lights, contact your utility. They have folks that will help out. What mitigation is in place? In other words, do I have backup generators, UPS systems? And don't assume those are always operating satisfactorily. So what I'm trying to do is, in this case, this graph I'm showing, I'm trying to drive down production losses or loss of use of equipment. But I also have to deal with possibly the increased cost as I take care of a higher and higher percentage of the problems. I have to take care of the increased cost that may come with knocking out more and more problems. So what I'm going to do is go out and start to gather information, build the pieces, put the pieces of the puzzle together. What do I have? What's working? What's not working? What kind of power tolerance do I have? Hook up the test leads to the equipment, do an inspection, look for loose connections, etc. So I'm going to define and log the problem, communicate with my utility and others in the organization, quantify the impact, investigate and inspect, test and measure as necessary. Of course, I want to correct the obvious problems, such as a loose connection. Then I start looking at my solution options and the cost of those versus the performance improvement I might receive. I evaluate my reliability and maintenance because is that system I'm going to look at putting in, such as mitigation equipment, is that UPS or that backup generator going to be reliable? How much do I have to spend to maintain it and operate it? Specify, install, and test and properly maintain the systems. Now, for an example, in a glass plant, we're able to actually go out and change and put in adjustable speed drives where they had standard motors. We're able to put in adjustable speed drives and to back up the controls because they were seeing when a breaker operated from the utility, the glass plant equipment would go down. They'd have molten glass that would harden their equipment. So in this case, we took the drive, although the side effect or side benefit was energy efficiency, their primary concern was the equipment going down, uncontrolled shutdowns. So we're able to install adjustable speed drives that could restart on the fly, back up their control systems, and we actually used that to solve the problem. So although one or two pieces of glass may have a little bit of inconsistency in the quality, that wasn't a major issue as compared to spending, let's say a half a day or a day cleaning out glass out of this equipment because it had an uncontrolled shutdown. Start and maintain a trouble log. How do we know when it's happening and what is happening in the facility unless we start to document it? So are we seeing these daily? For an example, when I started that project at the airport, when is it occurring? They say, well, every morning between 4 and 6. Immediately, I already had an idea of what was happening on the system based on when they told me it was happening. So how about you? If you're having a problem or your customer is having a problem or client, what time is the system going down? Maybe it's the startup of their chiller in their facility that's causing the issue. And maybe they start their chiller every morning at 7 a.m. So those are things, by documenting the power quality anomalies, we can help to become a sleuth in this whole process and document what's going on in the system. Also document the economic impact. You're going to see more participation from different personnel in your industry or organization when they see that this has a significant impact. I mean, if we're a multi-million-dollar organization and it costs us $50 a year, we're not going to nearly pay the same attention to that or put the same resources towards that if it costs us, let's say, $5,000 or $50,000 an event. Also, break down what is failing. Does my adjustable speed drive maybe give me a trip code saying over voltage or under voltage? It could be the emergency stop relay, a simple little relay that I might be able to replace with a more tolerant relay. And if you modify controls, please be careful of the safety concerns around controls. So in many cases, I don't have to go treat a whole all the power coming into the facility, treat a whole feeder. Sometimes I can go out to the controls and just treat a few amps worth of power by working on the control system. So it's important we look at what's going down and why. Here's an example, by the way. I've talked about power tolerances. This one manufacturer, they published, this is their power tolerance. 220 volts is what they said they wanted on the input. Well, that's a non-standard voltage in the US. Right away, that's a red flag for me. And they actually meant the 220 volts. So it said provide clean power. What's clean power? Please define that for me. How can I hit a target if I don't know what I'm trying to hit? In the upper right-hand corner, it kind of reminds me of a kid trying to hit a piñata with a blindfold on. Shall I just keep swinging here until I get it and hope I get it right? What is right? Okay, they said +6, -10%. Well, -10%, take 22 volts off of there. I'm sitting right about at my normal 208 voltage power delivery system. This equipment was not designed properly to operate on normal power systems within the U.S., even though it was designed by a U.S. manufacturer for U.S. markets. So what do we have to do here? We had to put a voltage boost auto transformer in the circuit. But this should have been taken care of. This should not have been purchased this way without an expectation of doing something initially. One industry group, the semiconductor industry, they have actually created immunity standards for SAG immunity for their equipment so that they have less problems with operating their equipment. So there's other problems, such as I've been to sites where they had contaminants. They had actually a carbon fiber manufacturing plant where they were seeing carbon fibers and carbon dust get into their equipment and actually causing faults or arcing to take place in their equipment. And they had actually thought that the utility was causing a voltage problem when it was actually contamination from their own manufacturing process. Operator error, software communication. These are all things that we need to sort out because they can be a part of a problem, an intermittent or damaging problem. So we have to look at weighing the options. Do we correct the existing system or do we install a new system? Just a quick case study on an adjustable speed drive. This cement plant, way at the end of a long feeder in a rural part of the U.S., they had adjustable speed drives that they had previously installed. They had to buy multi-million-dollar mitigation equipment to make them function properly. They were going to install additional drives. They wanted to know, do we have to install $1 million more worth of mitigation equipment? And looking at the installation, there was newer drive technology that was a lot more tolerant. It was more efficient, more tolerant. So rather than spend $1 million on adding to what you would call mitigation equipment or equipment that could make those drives operate, the simple solution here is go in, get a rebate, replace your existing drives, make sure the new drives are specified properly, and install those and test them and verify that they work properly. And they did. And so they saved over $1 million. They got brand new drives. Their drives were close to 10 years old. They were very excited. Those drives were more efficient, had better controls, and that was a simple solution to a complex problem, what could have been a complex problem. So sometimes we correct the existing system. Sometimes we look at new system installation. Now, I've just given you a list of some of the different types of mitigation options here. Equipment replacement, surge suppression, which should always be installed to protect systems against surges, power surges from causing failures. That should be the minimum basis for protection in a facility. Wiring changes, there's kind of a whole list here. And what you need in your particular installation may just be simple equipment replacement. If you're having issues, it could be a wiring correction, fixing a loose connection, or it could require some mitigation equipment. And I've shown you on this slide, we can see an example, the Institute of Electrical and Electronic Engineers. This is an example of the many modes or levels of surge suppression that they recommend in a facility to help protect against the transient overvoltages or power surges we talk about. And those are sub-cycles, so very short, brief duration, requires a specific monitor, power quality monitor to see them. These are very short-term anomalies in the system that can cause malfunctions or equipment breakdowns. When we look at installing, if we're going to install mitigation equipment, we need to ask ourselves, is this the right prescription? Is it appropriate? Is it efficient? Will there be side effects for the installation? What are the operating costs? We have to consider maintenance, repair, all those things around the installation. Am I buying the right piece of equipment? In some cases, we've had folks buy the equipment, it was not correct, and they ended up with what I would call a large paperweight. So always make sure, again, you define the performance criteria. As we see here, this equipment was not suitable for the installation and experienced multiple failures. So when we look at specs, a lot of times we'll look at a glossy sheet from a manufacturer. It may say, solves every problem in the world. Greatest thing. Some of the things we look at, the spec sheet says up to 95% efficient. That means anything between 0 and 95. So again, we need to write the performance definitions here and make sure we're getting the right equipment, because in many cases, literature is designed to sell equipment, not provide all the necessary information we need for performance. These are some examples of claims on manufacturer sheets. Sealed maintenance-free battery. There is no battery that's maintenance-free. 100% efficient UPS. Well, how does the UPS create all those BTUs of heat that you show on your spec sheet? Total lightning protection. Surge protection that provides interruption ride-through. So sometimes we'll see, especially in rural areas, people will come through with a new super device that saves energy, does everything, including washing dishes and mowing your lawn. Again, we have to be careful about those performance claims. Show me some scientific test data that backs up your claim. In some cases, these folks use a lot of testimonials, but they don't have any true scientific data to back those claims up. So when you're doing a site survey, always pay attention to safety issues, arc flash and shock hazards. So when you're going to hook up equipment, go out and do inspections, please pay attention to the safety issues so that you don't hurt yourself. Document, go out, take measurements, inspect the systems, document what you observe, what you measure, compare that against the National Electrical Code and power quality installation practices, such as described in the IEEE Emerald book or the IEEE Standard 519. Some typical equipment you may use are listed here, including power quality meters, wiring error meters. There's a whole host of equipment. Yes, even your trusty AM radio can help you find loose connections. You can hear the static on the AM radio. Very inexpensive tool that you can use to go out and look for loose connections. Power quality monitors. Now notice I have it underlined up here, power quality disturbance monitors. A lot of companies call these power quality disturbance analyzers. The monitor does not analyze the data, you do. The monitor gathers the data and presents it. So it's very important you understand how your monitor gathers data, what its capabilities are. If I take a data logger out there that's just used to gather information for how much loads on the system, generally it's not going to have the capability to look at higher speed events such as high-speed transients, or to look maybe at a cycle-by-cycle basis for sags. One monitor on the marketplace does not fit all applications, even when it comes to power quality, quote, analyzers. You need to look at the capabilities and understand, does it provide the level of monitoring capability that I need to look at what I'm trying to find? So there's different types of, there's monitors, there's load profilers, again, look at long-term data loggers, environmental instruments, and specialty instruments. So power line disturbance monitors typically used to capture this kind of information. So solutions, correct wiring errors, install new wiring systems, upgrade, replace utilization equipment, specify mitigation equipment if necessary, commission and recommission the system. And when you're looking, let's say you're going to install a backup generator, don't forget about disaster prevention issues. In other words, one site, they put all their generation, all their distribution equipment on the second floor, but they put their fuel tank right down there on the ground floor, where when they had a flood, the fuel tank floated away. Okay, so these are all types of things you need to consider when you're looking at power quality and reliability. Train equipment operators to make sure we don't have malfunction due to improper operation, and properly maintain the system. And here's kind of a list of resources here, your utility serving utility, the IEEE, the National Electrical Code, and training organizations. So in summary, most power quality issues can be avoided in the design specification of the phase through the proper selection and specification of equipment. It's really important that we understand the normal variations that take place on a power distribution system and specify and purchase equipment which can be acceptable, provide acceptable reliability and performance. I would highly recommend, if you have a facility or you work with a customer or client that has a facility, that they put power quality monitoring, fixed monitoring in place. It's kind of like a gas gauge, temperature monitor on your car. What is happening on the system? What kind of events? What's the range of fluctuation? So now later, if I'm going to go buy a new piece of equipment, I know what's happening on the system. So I can say, okay, this is the kind of fluctuations I need to be able to tolerate in my system. If you suspect that you're having a utility-related issue, please contact your utility and discuss this with them. They have a host of resources that can help you. And if necessary, install mitigation equipment. Just make sure it's the right equipment and weigh the return on investments, operating cost, maintenance, et cetera. If you have existing equipment that's experiencing a problem, conduct a thorough investigation. It may just be a simple loose connection in a wire. Document the information you gather. Meaningful information is always your friend. Always understand your monitor capabilities to make sure you're using the right monitor. Don't just throw expensive solutions at problems without understanding the real issues. I don't think anybody has money coming out their ears to be able to throw at problems today. And evaluate the return on investment. Well, I want to thank you for attending today, and I just wanted to provide PGE's Power Quality Hotline number here. So thank you so much for attending today. I appreciate it. And Lorena will provide additional information, including information on the upcoming class. So I'm going to hand it over to Lorena.
Great. Thank you, Gary. You did a great job of explaining what power quality is and why it's important for our business facilities. I wanted to give you a couple of reminders again before we go into the questions. If you want to ask a question over the phone, if you have access to that, feel free to use your raise hand icon and I will unmute you and you can ask the question. I do have some that were submitted through chat, and feel free to submit any other ones. We also want to remind you about the power quality course. It is a one-day course, and you do get 8 hours of continuing education units for your Oregon or Washington electrical license renewal. It also qualifies for the state of Washington basics classroom credits for trainees. If you want more information, let us know. And we have a special prize of $250 thanks to Gary and his partnership with us. Usually this class costs $400. So it's a great opportunity to take advantage of. We have more webinars and seminars, and you can also download some additional resources from our new website, the EnergyEducationCenter.com. And again, we'll send the recording and the questions after. If we don't get to all the questions, we'll have Gary reply to them, and then we'll send those to you guys. You'll also notice to the right side of your screen, there's a polling survey that came up. Please take a few minutes while we address the questions to give us your suggestions, your thoughts, and any other recommendations you have for this course. So Gary, the first question that came through, if a contractor is installing adjustable speed drives for a project that they have going on, are there certain questions that they should ask in order to avoid power quality issues?
Yes, Lorena, there are several, and you will be sending out that adjustable speed drive checklist. Lorena will be sending that out to you, which includes many of the questions you need to ask. Pass that on to your contractor and or vendor and have them review that checklist, and they should be able to address those questions. The NEMA adjustable speed drive application guide is also referenced in that document, which can provide additional answers and questions.
Thanks, Gary. How do you determine the direction of a power quality event? Can the equipment test determine if an event is a utility caused or customer caused?
It depends on the type of event. For an example, a voltage sag, if you have voltage and current that's being monitored and you have what's called a trend plot of those, you can determine whether it's upstream or downstream from the monitoring point. So some events you can easily determine whether it's utility caused or facility caused. Other events, let's say like a transient, are a little bit more difficult. It's what's called signature analysis, and there are signature analysis handbooks out there available from some monitor manufacturers. You can go on Amazon and just put power quality waveform analysis handbook and maybe get a guide.
Great. Another question is, should I have surge protection at home as well as at work?
Yes, it's very important to have surge protection any place we have electronic loads or things that could be damaged by a power surge. I have it at my service entrance to my home because I have adjustable speed drives that are in my furnace. I have a hot tub, etc., but I don't have a plug-in surge suppressor on. So I put it on the house at the service entrance, and I put it at the plug-in point of use locations to help protect the loads in my home, as well as that same application could occur in your business.
Great. Let's see, a technician servicing my equipment is indicating the recent malfunctions of equipment are related to poor power. How do I know if that is true?
Well, one of the things, if the technician's saying it's related to poor power, one of the first questions I ask the technician is to show me any data that they have that indicates it's poor power. And then I want them to tell me, to give me some kind of a published specification requirement, what type of power do they need coming into the equipment? In other words, what are the tolerances of the equipment? And at that point, once they give me the tolerances, I can perform power monitoring, if necessary, power quality monitoring and inspection to see, are the power tolerances of the power system that's being supplied to the equipment within the tolerances they say that they need to successfully operate. And that can become my gauge. But first of all, I need to get the tolerances of the equipment from them. If they can't give you that, then how can they say it's a power quality event? They can't tell you what it needs. Where's my target?
Great, thank you,
Very
Gary.
good question.
Thanks. And I did not see any other questions come through, and I didn't see anybody raising their hand to ask a question over the phone, but we will stay online a little bit longer if you have any other questions, suggestions, or recommendations. And thank you again, everyone, for joining us today.